which is now what?
1 minute, 59.
Now 1 minute? Holy crap, dude!
59 minutes and 40 seconds.
Yes, we have now broken the 2-hour mile mark. In the 1800s, now he broke it.
Circular course, no hills, and drafting the whole way.
He broke it. Right. What's now? And what was that one? Yeah, I mean, you gotta think about this. In the 1800s, we thought 4 hours would be fantastic. All right. So now the question is, when will the 1 hour 50-minute mark be broken, and the 1 hour 45-minute mark be broken? So, oh, and the other good, fun, exciting news, we're gonna have these to hand back to you. Okay, so we'll get those at the end. Okay. All right, so we're looking at cardiac physiology, trying to understand now what's going to be dealing with called cardiac output. We are going to take our cardiac output and look at it in two major ways. One is going to be heart rate, we have over here, right? Try that again, we have over here, and then stroke volume. We're going to walk you through the factors that affect each of these. We're going to very lightly touch on that one. So let's see what actually influences our total cardiac output. First thing is the autonomic aspect of your heart rate. We have the autonomic nervous system, which you remember is the sympathetic and parasympathetic, which you remember comes from the thalamus, which you remember then if it's the parasympathetic, it uses acetylcholine, and if it's the sympathetic, it'll use norepinephrine or epinephrine sometimes. So we need to look at how I can make my heart speed up and slow down, things that affect heart rate. So if you remember from the medulla, it had all these clusters of nuclei in there. And one group was called the cardiac center, another one was called the vascular center. And so we have, the cardiac portion was called the cardio-inhibitory center. And I can pretty much guess what it's going to do, because the name tells me its job, right, to slow down, to inhibit the heart rate. Now all you remember is that the parasympathetic branch is the one that does that. And now we got to see where that comes from. We're going to come up here. We always read the diagrams first and get our bearings. So there's my medulla. And then we're looking for the idea of the parasympathetic and sympathetic. So I labeled in purple the parasympathetic branch, so we can trace it backwards. And it's going to come from the cardio-inhibitory center of my medulla. I remember that. Okay, great. We're going to be using the vagus nerve, which you will learn. That's going to come down and innervate the SA node and the AV node. Now, if I were looking at this, I'd realize, well, wait a minute. I actually have three different groups of myogenic cells, the SA, the AV, and the Purkinje fibers. And this thing is designed to slow down my heart rate. I understand why it's going to the SA node, because what is its natural tendency? 80 to 100, okay, so I want to slow that down. I want to slow down my 40 to 60s, but apparently evolution didn't let a branch go down to the Purkinjes, because does anybody remember how slow they were going?
20.
Yeah, they're already slow. I don't need to slow them down anymore, right? Slow is slow. So I memorized this idea, right? Then I go, well, if I have a cardio-inhibitory center, then what's the opposite of that? The cardio-acceleratory center. So I look at that, and again, looking at my medulla, I'm going, okay, so there's the acceleratory center, and it's going to go down through the sympathetic cardiac nerve. Don't worry about the spinal cord portion, right? We're going to go from the cardio-acceleratory center to the sympathetic cardiac nerve, and then I realized this one innervates the SA, the AV, and my Purkinjes. So apparently it's more important to speed everybody up than to slow everybody down. All right. So I remember that the sympathetic uses norepinephrine, the parasympathetic uses acetylcholine. Does anybody remember the type of receptors for acetylcholine? Muscarinic. Very good. And the other one was nicotinic, but muscarinic is just for the cardiac. So muscarinic receptors up here. And we'll talk about these sympathetic ones in a moment.
Do you want to slow down the AV node because it's getting its signal from the SA node?
Well, it's just sort of a redundant pathway.
Okay.
Just auxiliary backup.
Okay.
Might as well send both to them.
And you can have an actual heart rate that's full of 60, a resting heart rate. And if like
You
you
could,
sit
yeah.
athlete at 35, it might be biologically advantageous to be able to slow that. So it's not getting ahead of the SA node.
Yeah. But if you send an impulse down one branch, everybody gets communicated. So you can't just send one to the AV or one to the SA. Once I come down that vagus nerve, right, everybody that branches off is gonna get the same message. It's like a party line.
Okay.
You guys know what a party line is? Maybe older if you guys know what a party line is anymore. Okay, let's see how this works. All right, norepinephrine binding to cell membrane-bound receptor. Oh God, that sounds familiar. Is this a lipid soluble or a water soluble? All right, it's water soluble.
G protein.
Lands on a beta-1 adrenergic receptor. That's the name you learn. All right, so norepinephrine lands on a beta-1. And we're gonna just keep it simple, but you actually know all this already, right? What I really want you to get from this is, bottom line, we end up opening calcium channels to let calcium come in. Now, what will that do to the membrane potential? So, Haley, that means, when you do this, what does that mean?
Go back.
Potential-
Increase it.
Become more positive or more negative? More positive. Okay, that's why I'm asking, just to make sure, okay. Now, what else do you know that calcium could be involved in? Besides changing membrane potentials, what else do you guys remember that calcium plays a role in?
You can open channels, right?
Open up channels, what else? Think 241. How about muscle contraction? So it lands on troponin complexes. All right, that sound familiar? Because they're going to do that too. So this calcium has a double bang to it. I make the membrane more positive, but I will also lead to a stronger contraction because I can land on troponin, allow myosin to grab, and increase my ventricular force. Right now, we're only looking at from the perspective, though, of heart rates. So don't worry about everything else down below here, right? If you remember it, that's awesome, but that's not the focus of this slide. The focus is norepinephrine on a beta-1, leading to increase in calcium flow, making the membrane more positive, because then I can look at it in this context. We're looking at three different graphs here. Notice the x-axis is the same for all three, so we're comparing one graph to another to another. The very top one up here says normal resting, and nobody say this out loud. Don't say it out loud, but can you tell me which action potential you're looking at? Which action potential is that? Like I said, don't say it out loud. Now you owe me 3 pineapple cheeseburgers. All right? Did you guys say myogenics in your head or an SA node? You should have. That's what it is. Because you recognize the pattern. We got to recognize the patterns. How many action potentials do we have on that top graph? Ladies and gentlemen,
4.
how many do we have? We have 1, 2, 3, we have 4. Okay. It is what it is. You have 4. Okay, now, you don't need to memorize actual values. But we're going to shake a cobweb maybe from math class. The area under the curve. Look at the amount of purple shading we have as a way of visualizing this. So there's normal, right? My threshold value where I remember my voltage-gated calcium channels open up. And my membrane's at -60. This is normal. I get 4 action potentials. Now what if I apply acetylcholine, which will, come here, increase potassium permeability? Nobody say anything out loud. Those are only 6 cheeseburgers. So that should begin to talk to you. Potassium permeability. Which way will potassium go? In or out of a cell? Out. Scott, what does that mean? Out. It's going out. That, you guys are way too quiet. You give me heart attacks. Do you guys remember that potassium always goes out of a cell, except for maybe some other part of your brain? All right. Then when potassium leaves, what happens to the membrane potential? It becomes more negative, right? Okay, and we can see this. Normal is -60, but increasing permeability for potassium, it made it slightly more negative. There's more area under the curve now. Look at the slope, right? Making the membrane more negative means it takes longer to reach threshold. Therefore, in the same amount of time, I'll have fewer action potentials. I have slowed the heart rate down. Everybody okay with that one? Yeah? Okay. So now what if I make the membrane slightly more positive? What if I let maybe some sodium in or some calcium ions? Any cation ion will do, as long as it goes into the cell. Right? If -60 is normal, well now I realize I'm a little closer to threshold. the amount of purple is less than the original normal graph. Therefore, it takes me less time to reach threshold, so I can get one extra action potential in. I get 1, 2, 3, 4, oh, I get 5 in the same amount of time. Now I have a faster heart rate. And so this shows me how that was possible, right? Norepinephrine on a beta 1, calcium influx, cell becomes more positive, or positive means takes less time to reach threshold, and I'm done. So you should have recognized this was a myogenic contraction. Then the idea of having potassium leave, making the membrane more negative, should make sense to you. Having a positive charge ion come in, usually calcium or sodium, should make the membrane slightly more positive, therefore I can get more signals in the same amount of time compared to normal.
So with norepinephrine and an increase in permeability, there's still potassium that's going to leave the cell, but more positive
Yep.
charges are coming. Okay.
Yep. Remember, you always have leaky channels too as well.
Yeah.
With this. All right, is everybody okay with that? Okay, so let's look at this then. That's the first way I can change my heart rate, right? Through the implementation of my either cardio-inhibitory or cardio-acceleratory centers from the medulla using the parasympathetic and sympathetic acetylcholine and norepinephrine. The next category that raises your heart rate is called the cardiac reflex. So think about what reflexes are, these instantaneous changes or responses to a stimulus. What kind of reflex are we talking about? Well, think about where you have the internal carotid, you know where that is. Think about the arc of the aorta and your right atrium. And in those locations, we have two massive cells. One mass we're going to call a baroreceptor. Another mass we're going to call chemoreceptors. Well, what does baro make you think of? And what is barometric pressure? It's just pressure, right? These are pressure sensors. They're going to measure blood pressure, or they'll respond to blood pressure. What do you think a chemoreceptor will respond to? Chemo meaning chemicals. So O2 and CO2 and hydrogen ions are chemicals that these guys are going to respond to. All right, so the name tells me what they're responding to. Now the question is, what are they going to do when they're doing their job? Baroreceptors, when they sense high blood pressure or increases in blood pressure, will lead to a decrease in heart rate. So increase in BP leads to a decrease in HR, if you want to abbreviate it.
Say that more time.
Increase in BP.
Increase in blood pressure, Haley, leads to a decrease in heart rate. Now, once you memorize that is a memorizing task. Great. What's the logical opposite of that? How about a drop in BP, which would cause what? An increase in heart rate. They're inversely related. That's easy to remember. So increase BP, drop heart rate. Lower BP, raise heart. So I want to keep the same amount going. Now, chemoreceptors, right, will measure oxygen, CO2, and pH, which will be hydrogen ions. So now if you're low on O2, that's going to increase your heart rate. If you're low on O2, you're going to increase your heart rate. Because you want to send more of that poor quality blood faster. Which makes sense. Now, in case you don't know, you're going to know this. That the amount of O2 normally is opposite to that of CO2. If you're low in O2, you're going to be making lots of CO2. So if I'm low in O2, I will be high in CO2. I want to get rid of that CO2. I want to distribute my low O2 as fast as possible. So both of these lead to an increase in heart rates. What if you're high in O2? What happens to heart rate? It's going to slow down, right? So once you memorize one, the other one is just nice and logical. What's funny was I actually had some downtime last night, and I had Sunday Night Football on as background noise. And Chris Collinsworth, one of the commentators, was looking at an athlete who just came off, or a football player, just came off the football field. He sits down, he grabs an O2, and he says, that isn't going to do a damn thing for him. And it's very true, right? Giving yourself oxygen isn't really going to make you recuperate that much faster. It does help to kind of calm you down a little bit. It kind of helps to lower your heart rate. But in terms of recovery, he's already cardiovascularly fit enough that he's not going to get any benefit from this. It was just funny to see a commentator actually now make that kind of a comment on there. So you pause, you go, wait, okay, I have now two major categories, ways of making my heart rate change. I can use the autonomic nervous system, or I can use cardiac reflexes with the involvement of baroreceptors and chemoreceptors. Both of those receptors are found in the carotid, the aorta, and the right atrium, measuring blood pressure and gas values of my blood. You memorize that first before we go on to the next one, because there's a lot of information on these slides. This is just pure memory. This one's a little bit of understanding and logic to it, right? But again, it's pure memory.
Can I ask you a question before I cover really quickly? So if the guy takes a bunch of oxygen, wouldn't he actually mess up that reflex if what he's trying to do is flush the carbon dioxide? Because now he's going to slow himself down and he's not going to get rid of
Not
the
really,
carbon
because we'll talk
dioxide.
about the carrying capacity of our hemoglobin and pH a bit later. So for the time he's using it, he only uses it for like 5 seconds. More talking like giving a baby a pacifier just to feel comfortable. He was a big baby.
Can I ask you a question about this slide? On under the chemoreceptors, the response to low 2 and high CO2, did you say that would cause an increase in heart rate?
Yes, because you want to speed the lower quality blood around faster. And this will actually lead to increase in hydrogen ions. I want to get rid of it as fast as I can. So both it makes sense to speed the heart rate and get rid of it as fast as you can.
Okay, and then the opposite would be like slowing your breathing down, and it can bring your heart rate down as well. Correct? You can cause your heart rate to slow by taking.
And that'll also lead to an increase in the force of a contraction a bit later, but yes. So people who are trying to meditate will slow their breathing to lower their heart rate and make themselves more calm and more centered. But they're changing heart rate for stroke volume. So they're changing rate for force to do that. Which we'll kind of get into a little bit toward the end. All right, here's the third way of changing my heart rate. All right, again, one slide at a time. This is known as the atrial reflex. Some books call it the Bainbridge reflex. All right, now, adjust heart rate in response to venous return. Let's take that apart. What is venous return? What is venous blood? It's the blood coming to the heart. So really, it's about how much blood comes into the right atrium. That's going to be our determining factor. Blood coming into the right atrium. Now, I want you to put a big asterisk somewhere next to this in your notes. Right? The atrial reflex is about increasing or changing heart rate. It's about changing heart rate. Underline that exclamation point. Right? It is not about force. This is only about heart rate, not about force. Put a big asterisk next to it, highlight in yellow. So how does this deal with an increase or a change in heart rate? Picture your right atrium as a balloon that has not been inflated. If I blow air into my balloon, which represents blood volume, what happens to the size of my balloon? It's going to get bigger, right? The walls are going to stretch. So in the walls of the atrium are stretch receptors. And they're measuring how much stretch they're experiencing. And when they experience stretch, they're going to send a signal through the sympathetic pathway from the cardial acceleratory center. So you're going to have, basically, you're kind of thinking of an idea of, I want to dirty up that. I'll dirty it up right here. Let's see if this works. I'm going to have stretch receptors in here. I can think of a nerve. It's going to go up to my brain, to my medulla oblongata, and then it's going to send a sympathetic nerve right back. So I can then make my heart rate go faster. So if you're using this, that means I'm going to send a signal all the way up to my cardial acceleratory center. It's going to come down my sympathetic cardiac nerve, release norepinephrine onto beta-1 adrenergic receptors, causing more calcium to come into the cells, increasing their membrane potential so it takes less time to reach threshold, and that is how I get an increase in heart rates. The atrial reflex is taking advantage of this. All right? So it does involve the sympathetic nervous pathway. Remember, this involves heart rate. not force of contraction. And we're going to take a 5-minute break. You guys go outside, get some cool air. Come back and look at the autonomic, cardiac reflex, and this one. And if you have any questions about any of them, ask now before we go on and add more information to this pile of information. So go get some cool air, come back in about 5 minutes.